Thank you for the kind introduction. Good afternoon, everyone. Thank you for coming to my presentation. My name is Byeon from Seongwook University, South Korea. Today, I present our paper, Avalanche, Optimizing Cache Utilization via Matrix Reordering for Sparse Matrix Multiplication Accelerator. Let's begin. I introduce our research in the following order. And first, let's start with the background. Background covers the outer product data flow and tiling algorithm. As you know, sparse matrix multiplication is important operation in many applications. However, high sparsity leads to low operational intensity. It makes it challenging to accelerate. To address this issue, outer product is one of the promising solutions. Because outer product has high input matrix reusability, it is suitable for memory-intensive operation like sparse matrix multiplication. Let's see the outer product data flow with example. Outer product performs the multiplication between one column from matrix A and one row from matrix B and generate the partial matrix. This partial matrix becomes to intermediate matrix and used for further computation. Next, we move to second column row pair. We perform the multiplication between second column from matrix A and second row from matrix B and generate the partial matrix. This partial matrix is merged with the intermediate matrix. The third column row pair also perform the same operation. And partial matrix also merged with the intermediate matrix. This operation is repeated every column row pair in the matrix. The key advantage of the outer product is excellent input matrix reusability. Outer product requires each column row pair only once. However, outer product exhibits the low output matrix reusability. Each column row pair generates a substantial number of partial matrices, which then require matrix-wise merge operation, leading to considerable memory traffic. This example illustrates the limitation of outer product. We assume that on-chip memory can store 4 non-zero values. Like the previous example, first column row pair generates the partial matrix, and remaining on-chip memory capacity is 2. And second column row pair also generates the partial matrix and merge with the intermediate matrix. However, at third column row pair computation, no more available on-chip memory space. In this case, some product must be written back to off-chip memory, incurring memory store traffic. Following this, the merge operation can be performed. Similarly, the first column row pair computation also faces limited on-chip memory capacity. Again, some product written back to off-chip memory. In the worst case, some product stored in off-chip memory may need to be reloaded for merge operation, incurring additional load memory traffic. Finally, the result matrix is stored in off-chip memory. This example shows the low output matrix reusability of outer product. To address low output matrix reusability, one of the major approaches is matrix tiling. Flyawalk proposed the matrix tiling by predicting the number of partial products to be stored in on-chip memory. For example, let's consider the 4 partial matrices in the previous example. Tiling starts by counting the non-zero values in row 1, which is 2. The same process is performed for row 2, and we get the value of 2. This process is repeated for all remaining rows, and we get the 3 and 1 for row 3 and row 4. Then, matrix A split into row-wise tile based on this expected number of partial products. The tiling algorithm ensures that its expected number of partial products for each tile does not exceed the on-chip memory capacity. If you assume that on-chip memory capacity is 4, matrix A split into 2 tiles. First tile has 4 expected number of partial products, and second tile also has 4 expected number of partial products. Consequently, intermediate matrices are reused within the on-chip memory, thereby enhancing their reusability. Next is key observations and our goal. In this section, we'll introduce 3 key observations we found and based on this, explain our goal. Our first key observation is increased metric speed traffic due to tiling. The tiling algorithm enhanced the output matrix reusability. However, it simultaneously breaks the perfect matrix B reusability. For example, matrix B used for first tile computation. However, matrix B used again for second tile computation. In the worst case, matrix B used for every tile computation incur excessive memory traffic. This figure illustrates the memory traffic for matrix B according to the number of tiles. On average, matrix B traffic increased by 6 times approximately when number of tiles is 32. Therefore, reusing matrix B within the on-chip memory is crucial to achieve the optimal performance. Second key observation is on-chip memory underutilization. During the tiling, mismatch can occur between expected and real number of partial product. And this mismatch can underutilize the on-chip memory. For example, expected number of partial product is 2231 for each loss. However, real number of partial product is 1231. In this example, expected and real number of partial product in row 1 are mismatched. When on-chip memory capacity is full, we expect that tile 1 has no memory underutilization. However, tile 1 actually has memory underutilization of 1. This is because the merge operation. Merge operation combines multiple partial products into a single product. This results lower number of partial products than initially expected. On the graph shows the average on-chip memory utilization for 19 sparse matrix. On average, the tiled outer products suffer from 52% on-chip memory underutilization. The final observation is flavorance of dead product. Dead product means an output product that completes each computation earlier. In sparse matrix multiplication, each output product has different computation requirement. For example, in dense matrix multiplication, every output product needs 4 multiplication and 3 addition. However, in sparse matrix multiplication, some products require 2 multiplication and 1 addition, and the other only need 1 multiplication. This feature allows some output product may complete their computation earlier than the other, and we call this product as dead product. This example shows the dead product occurrence during the computation process. In first column row fair computation, row 2 of intermediate matrix no longer need immediately become dead. And during the second column row fair computation, row 4 become dead. And at the first column row fair computation, all remaining rows become dead. These dead products are not used in subsequent computation, wasting on-chip memory capacity. On the graph shows the proportion of dead and right product in on-chip memory. On average, 32% of products stored in on-chip memory are dead product and waste on-chip memory. Let's briefly summarize the key observations. First is increased matrix speed traffic. Second, on-chip memory underutilization. And third, prevalence of dead product. Based on this, our goal is to address the underutilization and dead product issue, making available space in the on-chip memory. Then, we'll utilize this space for caching matrix speed data, thereby reducing matrix speed traffic and enhancing the performance. Next is our technique, Avalanche. Avalanche consists of 3 key techniques: matrix reordering, dead product array evict, and reuse distance-aware caching. First technique is matrix reordering. The main limitation of detecting dead product is that dead products are generated randomly. For example, First column row pair highlight in purple generate the product and row 4 and row 5. Second and third pair computation are same. But during the first pair computation, row 6 become dead. Subsequently, during the remaining column row pair computation, each row become dead. This example clearly shows the highly random occurrence of that product. Matrix reordering rearranges the column of matrix A to enable the quick and sequential dead product generation. Let's check this through example. Unlike before, row 1 and row 2 become dead during the first and second pair computation. And row 3 become dead with first pair computation. Subsequently, the remaining row sequentially become dead. Therefore, dead product are generated from top to bottom. We can predict the dead product occurrence and enable low-cost detection. Second key technique is dead product array evic called DP evic. Despite the prevalence of dead product in on-chip memory, write product can be evic instead of dead product. To demonstrate this problem, let's look at an example. When on-chip memory is full, contention occurs between write and dead product, selecting write product as victim. And eviction of write product generates memory store traffic overhead. However, write product requires substantial computation, so they must be reloaded into the on-chip memory. Finally, when write product becomes a dead product, it must be written back to off-chip memory again. Sum up, the eviction of write product generates at least 3 additional memory traffic, 2 write and 1 read. The DP evic has 2 main goals. First, we evict the dead product, making available on-chip memory space. Second, reduce the contention to minimize write product eviction. For example, DP evic explicitly evict the dead product and make available free space. And this free space ensures write product can be stored without the contention. By leveraging Reorder and DP evic, we can make more available on-chip memory space. Under figure shows proportion of write product between conventional auto product and Avalanche. On average, Avalanche make additional space by converting 66% write product into dead product and evicting them. The last key technique is reduced distance aware caching, called RM caching. Avalanche make available space through Reorder and DP evic, and RM caching aim to improve the performance by storing matrix B data in this space. RM caching only stores matrix B data most likely to be accessed in subsequent tile computation. For example, during tile 1 computation, each column of matrix A multiply each corresponding matrix B row. Similarly, tile 2 computation is performed the same as before. We can see that second and first row of matrix B are used across both tile computation. Therefore, RM caching in this example only stores row 2 and row 4. We define reduced distance to quantify how much matrix B is reused. Reduced distance refers to number of tiles between current and subsequent used. Under figure shows the proportion of reused matrix B data when reused distance is 1. On average, 40% matrix B data is reused in adjacent tile. This inter-tile matrix B reusability enables significant performance improvement. To implement our 3 key techniques, we propose the Avalanche architecture. Avalanche architecture consists of 4 main components: matrix fetcher, job allocator, and processing lane, and unified cache. For detailed implementation, we kindly ask you to refer to our paper. Next, evaluation. For our evaluation, we compare Avalanche with the Spaghetti and Gamma, which are state-of-the-art auto product and low-wise product-based accelerator. All three accelerators were evaluated using the same hardware configuration, 16 processing element, 16 merge unit, and 2 MB on-chip memory. We select the 19 sparse metrics to cover diverse characteristics such as density, dimension, matrix shape, and input matrix reusability. The area of Avalanche is 6.1 square millimeter. From our performance evaluation, Avalanche approximately 2x performance improvement compared to Spaghetti and approximately 20% speed up compared to Gamma. Furthermore, Avalanche shows about 50% reduction in memory traffic compared to Spaghetti and Gamma. Our paper provides additional detail of hardware implementation, in-depth evaluation, and matrix reordering method. If you have any interest, I ask you to refer to our paper for more information. Finally, I would like to summarize this presentation. We found three key observations of tiled auto product: increased matrix speed traffic, on-chip memory underutilization, and prevalence dead product. Avalanche addressed a aforementioned issue by leveraging three key techniques: Matr and DP-EBIC and RM caching to make available on-chip memory space and caching matrix speed data. As a result, Avalanche achieved 20% performance improvement and 50% reduction in memory traffic. Thank you for your attention, and if you have any question, feel free to ask me.